We saw in the previous tutorial on the heliceal multirotor interface, how to create contra-rotating propellers, which bring together in the same interface, the performances and geometry of two interacting propellers. That's for contra-rotating propellers, but the multirotor interface has another very interesting function. This is the possibility of creating multirotors on the same plane, with or without contra-rotating propellers. This is what we will see immediately. So we return to the general heliceal interface, and we will load a model for multirotors which will be based on smaller series. Here we have an airplane propeller. We will select a classic propeller for FPV drones. And here, we are going to take a 5-inch propeller drilled to 5 mm. It is a classic CPV propeller like you can find on the market. When we select a model in the list of our models, here, we have the information on the propeller model and we can see the pitch. So for information, for those who are used to working with drone propellers, the pitch is the pitch angle. The pitch, that is to say the distance that the propeller would travel, if it was screwed into a solid like a screw into a nut. So commercial propellers are often given with pitch only. Here, in inches, here a propeller with a pitch of 2.6 inches. But we can see that unlike commercial propellers, we see that the pitch is not identical across the entire propeller. That is to say that in fact we will have a less important step here, at the base, and a more important step here, at the end. This comes from the fact that normally the pitch is constant on a propeller, if it is calculated fairly basically. The heliceal software uses a calculation method, which is BEM, blade elements momentum, which incorporates the induced axial and tangential speeds, and which ensures that the angle of incidence with which the propeller will work at any point within its radius will be optimum and will provide optimum performance depending on the optimum finesse of the selected profile. So the step is slightly different because we calculate the induced speeds. Here is this little detail for connoisseurs in terms of propeller design. So here we are going to take for this example a 5-inch propeller and we are going to try to produce specifications for a multirotor with this propeller. So we loaded and 5 inches. But for your information, if we had directly selected the multirotor project interface in the file menu, we have a small prompt which offers us to load it automatically. So that was the 5 inches that we see here at a certain operating point, which is 25,000 revolutions per minute at 0 meters per second. So this means that this propeller has the best performance at 25,000 revolutions. For a fixed point, that is to say the drone is not moving. Being just in lift, it would be a lift propeller which would therefore have optimized performance for the hovering. We could very well take this propeller and modify its operating point and say, hey, I want this list to be made for a flight of 20 meters per second, and rebuild it according to these new specifications, and therefore start with a situation where we would have a propeller that has been optimized for flight at 72 km/h 20 meters second. So we see that we can take any propeller, let's say basic, modify its geometry for a new project. So here we are going to stay on a propeller that was based for hovering, so 0. So we cannot have absolute 0, we are going towards 0.01. We will therefore see how to incorporate this propeller into a new FPV project. So after selecting the propeller, we just need to load the multirotor project propeller. So here if we had changed the geometry, we would have to select Yes, use this new propeller. If we want to load a default propeller, we click No, and it will be the default 5-inch drone propeller. Yes. So this opens the multi-rotor interface with the multi-rotor frame option. That is to say that we will have several propellers rotating in opposite directions, gathered around a frame. We will see here by selecting the parameters of the frame, here on the right. And we therefore have, for example, the number of arms which can be modified. Therefore the number of propellers, the lengths of the diagonal. We are going to put a larger diagonal of 600. And so there we could consider building VTVLs, vertical takeoff vehicles. With a given load, that is to say a weight of the frame which would be. We are going to put 1500 grams, so we can configure our frame and add modules, that is to say we can add the camera here. We're going to add a small camera module, okay, so for now the camera. Just about anywhere. So the frame, we can also modify its length, its width. We can say that it is 80. And so we could add modules as desired to modify the load of our vertical takeoff vehicles. The engines, so here we see in the frame settings, the definition of the engines. Then we can modify their diameter, their height and their weight. This is more for checks at the geometry level, or even that we don't do anything, that the engine is not disproportionately large in relation to the propeller. Depending on the kV and the number of battery cells. Therefore, depending on the voltage, we can very quickly obtain the rotation speed, which will of course have to be implemented here, in the operating point, to check the final operation. For frame, that's about it. The rest is pretty logical. We will say in terms of sizing, there is nothing special. We can modify the thickness of the arms, the thickness of the frame, etc. So that's it. All the parameters of the frame with motor. We will go back to a classic 4-arm FPV, like that. Now we have seen the frame settings, we will see the geometry propellers. So here we can select modify the geometry of our thruster. We're going to slow down the rotation speed a little. We could show here, in the view menu, the axial induced speeds and the vortex losses. We are going to modify the frame a little and put smaller arms. Of length rather 400. Let's admit. And therefore we could increase the size of the propeller at this level or edit it to modify it as desired. Our list of basics here, so for example, I could say, I want a propeller that a little bit more with a little bit more Greek. So then that's not what I want to optimize. I would like to get its geometry. And we will give it the shape of a curved generator. With a little bit of curvature. Like that. Here the curvature of the generator does not modify the performance of the propeller, it is simply in terms of operation. It will tend to be less noisy because it will not have crossings. If it passes in front of the arm, for example, it will not have the whole blade which will strike aerodynamically in front of an obstacle. It will have a progressive attack on obstacles. So it tends to make a little less noise. This for our drones, so you see how I modified in the initial interface, and I return here via this menu in my multi-rotor drone interface. And here our propeller has simply been modified. So in this multi-rotor interface, we also have on the left, therefore, the possibility of modifying the operating point. I could say, I want a propeller system that will move, no longer in a fixed point, stationary, but at a certain speed. And so I would like to calculate the propellers, for example, to do 20 meters per second. So here, when we modified the operating point, we see, as we see in the classic interface. So a quick digression before starting this tutorial. You must have already seen the tutorials on propeller design with Heliseal. This tutorial assumes that you are already familiar with the concept of performance, out design and new design. So the operating point here is going to be changed. We would have the possibility of recalculating the performance of these propellers, either in out design, which we are going to do right away. So there we have performance calculations. So we see, for example, here that there is quite a bit of red. That, in general, is a pretty bad sign. This is when the weight here, which is 1.6 kilos here, is greater than the propulsion of the propellers. So here, in vertical acceleration, we are in negative. That means we can't lift. So at this point, we can reconstruct the twist of our propellers at the new operating point, and we therefore obtain another twist, which is optimized for this speed. We see that we have more lift, that we have gone over the weight of 1.69 kilos. So we could of course add counter-rotating propellers to this project. Here, by selecting contra-rotating, the software will create contra-rotating propellers, which best recover the axial and tangential induction of the upstream propellers. So here, we see that we have greatly increased in terms of lift. This FPV drone therefore has a speed that has been studied, with propellers that are optimized for a flight of 72 km per hour. So to be precise, it's not really a flight of 72 km per hour, it's a speed upstream of the propellers of 72 km per hour. We are going to show the speeds induced in the propellers to clearly symbolize the direction of the fluid, which enters our propellers at 72 km per hour. So, in terms of visualization, we could also show the vortices at the ends of the blades, which would disappear if we were in a ducted propeller, nozzle propeller. This is just to clearly visualize the position of the drone. So 72 kilometers of air intake means that we have a vertical intake of 72 kilometers per hour. What we actually care about is the horizontal flight speed. And if we wanted to see what the horizontal flight capabilities of our device are, we can use here on the left in the multi-rotor project, the frame pitch zone, which gives us the possibility of putting pitch to the frame, therefore of putting some angle, and transform the vertical thrust into a horizontal thrust component, which allows horizontal acceleration. So we understood well there. So here we have the possibility to display the weight. Here are the weight vectors. So just to symbolize the vertical and the thrust vectors. So we're going to reduce the scales of the vectors for more aesthetics. So we have the thrusts here, which are therefore perpendicular to the propeller plane, which are parallel to the motor axis, and the weight, which here is the weight of the frame. When we select vectors in 3D space, we have the information displayed at the bottom of the screen. So here, if I select this vector which lights up in fluorescent green, we see here the force, weight of the frame, which is 8.35 Newton. Here in this configuration, we're going to modify it right away to have a weight. So I select the frame, and so in its information here, on the right, we have the weight, which is 850 grams. We are going to go to 1850 there. We are increasing the weight of the frame so that our example is more convincing. I am going to put myself back in view left, so that we can clearly see the pitch, and so we see here that if I change my pitch angle, I'm going to have my lift projections that are going to be more horizontal. So here on the right we will see the horizontal acceleration, which increases, the vertical acceleration which decreases. If I further increase my pitch, we observe that on the right, we will go into negative vertical acceleration. So that's about the maximum pitch we can apply to this frame before it starts to come back down. That is to say that if we add more pitch, we will have a frame which no longer supports the vertical weight, and which is in negative vertical acceleration, which descends. So this allows us to properly evaluate the maximum pitch that we can have with a certain lift and a certain frame mass. So in terms of pitch, we therefore also have the possibility of looking for the maximum pitch. So directly here set pitch max flyable. This simply implies the pitch generating zero vertical acceleration. So we see that with these conditions, the maximum pitch that we can operate is therefore 67 degrees. The drag of the frame, the drag of onboard objects, increases with speed. This drag will be a negative force which will subtract from the lift. So the more we accelerate, the more drag we create, and the lower the amount of lift and drag will be. We can thus reach the maximum flight speed, which generates a drag equal to the lift of the propellers. To obtain this maximum flight speed, we can do an iteration of tests until we obtain this maximum horizontal flight speed. So we'll see here. So I asked what is the maximum flight possible at 67 degrees. So this maximum flight will be reached when the vertical component becomes less than the weight. If we try to accelerate more, we will go down. So we no longer have enough lift, so we reach the maximum flight speed. So we see at the top here the speed parameter which is changing. The software is testing different speeds and detecting how quickly the drone will begin to descend. So the speed calculation is complete. The iteration converged towards a zero vertical speed, and we therefore have a maximum horizontal speed in these conditions of 75 km per hour. So with these propellers, and this rotation speed and this angle of pitch, we could also iterate to find the pitch that provides the greatest speed. So it's the same iteration, but in addition, we're going to iterate on the pitch. So it will be even longer. But we are still going to launch this iteration. For example, software has finished, iteration duration 15 minutes, searching for the maximum pitch, the pitch offering, the maximum horizontal speed, so here it would be 57 degrees, for 80 kilometers per hour. So be careful, this function is clearly time consuming, it takes a lot of time. This iteration lasted about 15 minutes. I shortened it, but it lasts about 15 minutes. So before selecting this, find max flyable horizontal speed pitch function, make sure that you have plenty of 15 minutes to let the software work quietly. So this area of functionality, here frame pitch allows you to obtain evaluations of the forces on your frame based on the pitch angle and a certain speed. So here we have a little graph which deserves to be detailed. Here, we see the drag, that is to say the trails of the different elements of our frame. Here, if we move with a speed that generates an upstream flow of 94 km per hour of 26 meters per second, our set of frames will cause disturbances and therefore drag forces that we will show here. Show drag vector, here symbolized. So we are going to detail the calculation of the drags a little bit. So here, for example, at this travel speed of 95 km/h, 26 meters second, we have a drag on the arms of 5.59 newtons. This drag therefore, which is the result of the interaction between the arm and the flow swept by the propeller, is largely dependent on the width of the arm. Here, it makes 25 mm cycles, but at 15 mm width. So build we will see that the drag, which was 5.59, increases to 4.15 on much thinner arms. So the parameter which largely influences the drag of the arms is the width of the arms, but also the speed of the flow leaving the propeller. The drag on the arms, and the only drag, we will say, which is not dependent only on the speed of movement. That is to say that if I have a movement speed here of 0.01, and I restart the performance calculation, I will see that my drag on the arms is 3.40 here, but the streaks on the frame modules and the camera module have gone down to 0.01, almost 0. So it's a logarithmic scale here on the trails to see clearly. Make sure all the trails match up. We see that between 3.40 and 0.01, there is a strong difference. So what happens is that the drag of the frame is only dependent on the speed of the flow that it encounters upstream. There is no flow generated by the propellers on the frame, and the same thing for the camera. It is only dependent on the flow generated by the speed, so we have a very low drag at very low speed for the modules and the frame. But the drag on the arm still remains quite significant, because it is really generated by the flow of the propeller, which we are going to model here. And so we can clearly see that whatever the speed upstream, even at a speed of zero displacement, we have a flow of propellers which induces a speed at the level of the arm, and therefore a drag which still remains significant whatever the overall movement speed. That's the small detail, in terms of drag calculations. So we have looked around the interface. Here we see that we can actually modify the rotation speeds independently. This is of little interest because in general we really start with an identical motor power supply and voltage. And in terms of calculations, it may be simpler and clearer to remain at identical rotation speeds on the rotary contracts. But for certain applications, it may be interesting to modify the speeds, so we retain the possibility of modifying this speed. We have gone around this multi-rotor interface more or less. We are going to remain at zero pitch. And we can therefore envisage the design of vertical takeoff vehicles in a fairly simple and fairly rapid manner. Thanks to this interface,